Good morning, everybody. My name is Ho. I'm from Linköping University Division of Automatic Control. And today I would like to talk a little bit about my research, what I have done so far and what's the ongoing research. So the title of my talk will be the modeling and fabrication for UAV. But I consider this problem is in the closed loop setup. So first, I would like to give you some motivation about that. So basically, we have a UAV system here, and this one is autopilot. It could be controller algorithm will be implementing this autopilot, and then this autopilot will give the calculated control signal into the actuator, and actuator reacts to give the correct control signal here to the UAV. But the point in your UAV, we have some noise. It's come from the process noise and also, for instance, it's come from turbulence. So it might change the operating condition of UAV. And also from the sensor, we have the measurement noise. So based on that, I think in the autopilot, or we can separate the state estimation or state observer from, we basically collect the measurement from the sensor, go through the state estimation, and we will have the estimated state. And the second thing is I want to consider the command given by the ground station sending to the UAV, and it will be one really useful signal in my work. So what is challenge for this problem? Basically, we have several challenges in because this system is operating in the closed loop system. So we have several issues because of this, and of course we have the cheap sensor. If you are talking to low-cost UAV, when you don't really have really good sensor, so it means that the measure signal here contain a kind of high noise, and of course we have some unknown parameter. So my research is try to find the consistent estimation for this parameter regarding the forward model and inverse model. I will go back to this kind of model later on. But for my research, I focus on the modeling of a quadcopter, and I consider the translation dynamic model. If we have the inertial coordinate frame, and we have body frame, basically the quadcopter contains four motor or four propeller. So the translation dynamic of a quadcopter is given by this equation. When we have this one, the derivative of the velocity. This one is the term related to the orientation of the body frame in the inertial frame. And this one is of course a gravity. This one is the thrust given by the propeller, and the most important dynamic phenomena in quadcopter is given by the last term is the drag coefficient. So we can model it by a constant multiplied with the velocity. And this table is detailed for the parameter here. So in my work, I already consider two models for quadcopters. The first one is a lateral model given by this equation. We can see that the last term here, the drag, is linearly dependent to the velocity, of the quadcopter. So this term, this coefficient is given by one constant divided by the mass of velocity, the mass of quadcopter. So it's turn out that we can estimate the mass of quadcopter if we can estimate this coefficient here. And basically in my work I consider only the measurement from IMU, and it's so in this setup I have the measurement from the row rate, and also I have the measurement from lateral acceleration here. And of course, if we write it in the transfer function form, so we basically have this transfer function where P is a differential operator. The second model I want to consider is vertical model of the quadcopter. When basically the normal model for the thrust is given by the thrust equal to a constant multiplied with the square of angular velocity of the propeller. But when the quadcopter is moving, so there is another effect by the translation velocity of the quadcopter, and it will contribute to the second term in the thrust model. The point that I'm working on system identification framework, so we would like to have kind of accurate model for the parameter estimation. So that's why we have to find the better, the more accurate model. And it turned out that we have another term in the thrust model here. But what is the difference between this? And of course, I have in this point, I have measurement from IMU, and also I have the measurement from the control block. So what's the difference between this problem and previous one? The point now we have two input, and these two input is calculated from one signal. So these two terms will be the measure from the control signal, and also these two terms will be correlated to each other. So from previous problem is a single input, single output problem, but now we have the multiple input, single output problem. So it's kind of more difficult to achieve the consistent estimate for the parameter. And so we already have the model for the system. So the question now is how can we achieve the consistent estimate for the parameter? Here I have three types of the system. Basically, in a normal case, we consider that we have only measurement noise, and we have the correct input signal. It means that you don't have noise in the input signal. And the second type of the system is we have more complicated the model when we have the process noise, WT here. And the last one is the most difficult one when we cannot access to the true control signal here. We have to measure it in some way. And also we have the process noise. And of course we have the measurement noise. And the one more problem in closed loop system is we try to feedback this signal into the controller. So this noise will be correlated with the WT, and maybe it will correlated with the noise in the control signal. So now the estimation problem will be even more complicated. So one solution in order to overcome this problem is to use instrumental variable estimation. But even we use IV method, I call it IV. Another problem is come to my research when it's possible if we try to estimate the inverse model because if you look at the sensor to sensor problem, we have, for instance, two measurements. One can be considered as the input, one can be considered as the output, but it's possible to switch this input output. So now the input will be the previous output, and that is give me to a different type of model here when now I have the noise-free output, but I have noisy input here. And the second thing is, of course, I have noisy output and I have noisy input. But as you know from previous slides, as we have a closed loop system, so this noise will be correlated with this noise and correlated with this noise. So the question here is, do we achieve anything when we consider the forward model and the inverse model? And here we have the closed loop system, so these noise are not independent, they are correlated to each other. So I want to give one example for that. Now for instance, if we consider an open loop system, when we have this transfer function, ut is input, and this is a noise model, and of course we can write the system in this transfer function form, more compact form. And now here I generate, I use a simulation data. When I generate the ET is the zero mean Gaussian noise, and I generate the input, the true input by this transfer function given by this Gaussian input with covariant 1. So this one, it should be UT0, but here I don't consider the noise in the control. So, and of course, if you inverse this model, you have this relation. The first coefficient here is given by this term. When we divide by 0.01, so we have 100. The second one will be given by this coefficient divided by this coefficient. So it's 99.5. And just if we use basically the least square, so this one is the ox model. So least square will give the consistent estimate for that, and also the maximum optimal covariant estimate. So here I have the estimate for, I use a Monte Carlo simulation for 1,000 run. And this one is the results obtained from the forward model. And this one is the results obtained from the inverse model. You can see that in the forward model, this coefficient, the mean estimate here is close to, similar to this one, the true one. And if you consider also standard deviation here, so this, from the statistic point of view, this estimate is consistent. But if you look at the inverse model here, you can see that the estimation results are completely unaccepted, because we can see that from statistic perspective, this is not constant estimate. But why do we have the problem in the inverse model here? Because the point, you can see that the output here is given by the input plus with the noise. So it means that the output is correlated with the noise. It is similar in the closed loop system when we have the correlation between the measurement noise, process noise, and the control input and the measurement, the output. So that's why we have this bias estimate. So in order to overcome this problem, we was considering the the IV method, but and also the closed loop problem. And this one already we submitted one paper to this conference. So I just want to show you some results from this. This table is quite different from this table, because if you divide this term by the 2 by 1 divided by this one, it will equal to this values. So that's why here I don't show 100 here, but I just want to show the model we obtain if we transform from the inverse model to the correct form of the forward model. So it turned out that if we use the IV method, we don't gain anything in terms of the mean estimate and the covariance estimate. It means that in IV framework, if you go from this way or the other way, it will be the same. So this problem is quite useful if you consider network when we have a lot of measurement, for instance. So it doesn't matter if you go from this node to another node, or you go from another node to this node. Because from simulation, I have really similar results. The difference is really small compared to mean estimate and standard deviation. So we can consider this difference will be the numerical error, because when you compute the estimation, you have to inverse some matrix. So it gives you some numerical error. And so I have to solve. I have one answer for the question of what do we gain when we go from the forward model and the inverse model. So now I want to apply this to the quadcopter. The problem is I consider is how to estimate the center of gravity of quadcopter if we have only the measurement from IMU. So I have also the same translation model compared to lateral model. And of course I have 2 measurements here from the IMU. But the lateral acceleration measurement here will contain one more term. It's the angular acceleration, the rho rate. And it will give us more high order transfer function. And from my lateral application, the output will be AY and the input is the rho rate. So now I consider the output now is the rho rate and the input is the AY. So the question here is, do I gain anything for that? As from simulation results, we see that doesn't gain anything, but we don't gain anything. But let's see for the experimental results. So of course, I describing the forward model using Euler transformation, and I have discrete time model like this. Here I have 6 parameters. And if we consider the inverse model, we have also 6 parameters. But you can see that this inverse model we have a causality problem here, when you see that the order of numerator is higher than the order of denominator. So it's a causality problem. That's why I want to consider, for instance, if we have the non-proper forward model, so we will have a strictly proper inverse model. So we can basically apply some adaptive estimation for the inverse model, but we cannot do it if we don't have a proper transfer function. So the output now will be the lateral acceleration, and the input will be the roll rate. Here is the signal I collected from the experimental data. When I have the first one is the command, the second one is the AY. We can see that we have several peaks here. It's the contribution of the angular acceleration. And we have the roll rate measurement here. And I collected the data for 34 seconds. Here is a table for the parameter estimation. So this one is the parameter I obtained from the forward model when I consider the roll rate as the output. And this one is the parameter I obtained for the inverse model. And this one is parameter for the forward model when I transform from the estimate of the inverse model. So it's turned out that you can see that the difference between these values are really small. So it's also shows that we don't gain anything if we consider the inverse model or the forward model in IV framework. And I think it's a nice thing for IV estimation method. And of course, from this value, I can compute the new center of gravity, and you can see that these two values compute the mean value compute from the forward model and the inverse model are really similar. The difference here, because we can see that the last digit is 3 and 4, is come from the numerical resource. So that's why we have slightly different results here. And this problem is the new question for my research is what can we do with the fault detection and isolation method. For instance, if we consider one, I think it's quite common in fault detection framework when we consider the extended adaptive multi-model estimation. When we consider, we use several filter. One try to capture one fault. So it's basically in this case, we use EKF, extended Kalman filter for that. And we have one hypothesis condition test in order to indicate which fault we detect. And for that, I go from the step of modeling when now I consider only the sensor fault. So I mean I have fault in the output. So here I have the model of the output given by the measurement plus with one term. And in this case, I have to extend the state vector for each EKF. I mean, I have the new state vector for that, and for that one, and for that one. In the new term will be the fault values. And here the sigma is indicate that if this term equal to 1, it indicate that we have the problem in this sensor. Otherwise, in the normal case, it should be equal to 0. So Mike, and for that, we can compute the probability of the fault happen in this sensor by using this equation. Is the Gaussian distribution, and from the EKF, this will be the innovation. S will be the innovation covariant matrix. And the goal for this work will be investigate the possibility to use a different measurement as the input and the output. It means that do I gain anything if I use this sensor as the input or I use this sensor as the output? But I still working on this problem, so I cannot give you the clear answer yet. But I just want to give one example for that. It means in here I consider 2 by 2 problem, and alpha is the angle of attack, Q is the PQ, the pitch rate, and of course we have delta as elevator control signal. So I just want to give you one simulation result. So in the normal case, we have the blue line here corresponding with the no fault case. It means that we don't have sensor fault. And I'm not sure if you can see this vertical line. It indicates that I simulate the fault happen in 8 seconds. And this the red curve indicates that we can detect successfully the fault around 9 seconds for the first sensor. And I achieved the similar results if I consider the second sensor. But this one is the motivation for the question is I want to investigate what do we gain when we consider the different sensor as a different input and output. So I just want to summarize the work and maybe show the future work. Is here I consider the problem of inverse model estimation that is useful in the sensor-to-sensor framework or in the network, because people have working extensively in the way that they want to select the input and the output in the network. So I think it's kind of a nice thing to show that in the IV framework we don't gain anything if we work from this way or the inverse way. And the future work, of course, I want to continue for more advanced of IV method to see the possibility in to get a more clear answer for this question, and try to use the same idea in fault detection framework. Thank you. Yeah.
You may have problems of
yeah. Yeah.
So in that case, what do you do?
For instance, in the forward model, basically if we use input-output, if we have the causality problem in the forward model, so we might use the new input as the output and the new output as the input. So it means that in the inverse model we don't have causality problem, right? Because we inverse it.
Usually it's the opposite.
Yeah, the opposite way. I mean, if in the forward model we have the causality problem, so in the inverse way we will not have the causality problem.
Yeah. The normal way, usually you have more problems in causality when you use the inverse problem than the follow.
Yeah.
But in that case, I guess it could still work if you don't do in real time.
Yeah, exactly. But in this case we cannot use some adaptive estimation for the forward model.
Some window.
Yeah, we have some delay for that. In this case we have delay for that. So that's why we come up with this idea, because we saw some causality problem in the forward model. So we want to investigate what do we gain if we use the inverse model instead of using the forward one. And it's turned out that we can have the adaptive estimation. I mean, we don't have causality problem. But in terms of the mean estimate and covariance estimate, we don't gain anything. So it's quite...
But that's just for that particular model.
No, it's not for the model, it's for the method. I mean, is this in this particular framework, the IV framework, we will have this nice property. But I'm not sure for another method in the estimation, another estimation method. I'm not sure that we will achieve the same thing.
So did you try with the experiments? Real data?
Yeah, I try with this.
What was with real?
This one is real data. So basically the point, the
Just have noise but not outliers or things like that.
now in that case we don't consider the outlier, because outlier will easily destroy the estimation performance. So in that case, actually we have more noise in this signal than this signal, because if you consider that the acceleration will have will be affected by the vibration from propeller and something like that. So we have the high, then more noise level here. So the natural way is people use less noise input and the more noise signal as the output. But we show that we don't gain anything if we use more noise signal as the input.
And your measurements are all from diameter, so you don't measure the RPM.
For this experiment, I collect only from ion measurement. Because the problem is I have a cheap platform to collect the data, so I cannot sure that my RPM sensor is good or not. So I try to use the best measurement I have. Yeah.